Yeah. Okay. Okay. So we've talked about the curvature tensor of a Riemannian manifold. Uh, so there were just a few things I wanted to say about the curvature tensor. So we saw some properties of the curvature tensor. It was determined by this function of four vectors, a multilinear function of four vectors, right? This bracket x, y, z, t is equal to the inner product of rxy acting on z, inner product with t, right? So remember, when xy were tangent vectors in TPM, then r of xy was an endomorphism of TPM, right? So this acts on a vector z to give another vector in TPM, and then you take the inner product with t, right? So this completely determines the curvature tensor R, okay? And we proved these properties of the this 4 tensor. Okay, so this is a multilinear function of 4 variables, so it's a 4 tensor. So we proved these properties. Okay. And once we have these properties, then we can define two very useful objects related to the curvature tensor. So one is what's called the sectional curvature. So let me explain what this is. So the sectional curvature is a function of two-dimensional subspaces of the tangent space. Okay, so suppose you take a point P in your Riemannian manifold M, and you take sigma, a two-dimensional subspace, of the tangent space at P. Okay. And suppose xy is a basis of this two-dimensional subspace sigma. Okay. So then you define the sectional curvature as follows. So first you define a quantity called the norm of x wedge y whole squared. So this is defined to be norm x squared, norm y squared, minus inner product xy squared. Okay. So this is greater than or equal to 0 by Cauchy-Schwarz inequality. And it is 0 if and only if the vectors xy are linearly dependent, but we're taking xy to be a basis. So therefore, this is going to be strictly positive. Okay. So this is actually strictly positive. Okay. So actually what this is that if you take the vector space TPM, then you can form what's called the wedge product of TPM with itself. Okay. And then x wedge y is an element of that wedge product. And the inner product on TPM induces an inner product on the wedge product of TPM with itself. And this is the norm squared for the induced inner product. Okay. But we don't need to know that. We just need this explicit expression for this norm of x wedge y squared. Okay. And then we define the sectional curvature. of the two planes sigma. So this is denoted by K of sigma. This is defined to be so inner product of R of xy acting on x, inner product with y, the whole thing divided by norm of x wedge y squared. Okay. And what one needs to check is that this is well defined, independent of the choice of basis of sigma. Okay. So that is because we can go from any basis xy to any other basis x prime y prime via the following operations. So one is you interchange the order of the basis elements. Xy goes to yx. Okay. So you can see that this numerator will not change sign if you interchange both x and y, right? Because we know that this thing is what? This is round bracket xy xy, right? So this 4 tensor, this is alternating in the first 2 arguments and also alternating in the last 2 arguments. So if I interchange both, then this doesn't change sign, right? It stays the same. Okay. And the denominator doesn't change if I interchange xy. So this expression is unchanged if I interchange x and y. Also, if I say multiply one of the 2 vectors by a non-zero scalar, say x alpha y, okay, alpha non-zero, right? Because you'll get an alpha squared coming out in the numerator and an alpha squared in the denominator, so those will cancel. So this is unchanged. And then the last operation is xy goes to x plus alpha y, comma y, right? Okay. So we can get from any basis to any other basis via these elementary operations, right? And the last one you can also check does not change the curvature tensor. Okay. I mean, this expression for the sectional curvature is unchanged under this last operation. Okay. So, I mean, to see this last statement, if you look at, say, x comma, what is it? Sorry. If I look at yeah, so x plus alpha y x plus alpha y right. So then if I expand this by multilinearity, what will I get? I'll get terms xy x plus alpha y plus alpha y x plus alpha y. And now here in the second term, I have two y's. And so this becomes 0, right? So because it's alternating in the first two arguments. So alternating in first two arguments. So therefore, this is equal to 0. And similarly, this term, because it's alternating in the last two arguments, you'll get xy plus alpha xy y. And again, because it's alternating in the last two arguments, that means that this term is 0. And so this curvature tensor remains unchanged under this operation. So this becomes just xy. Okay. And I leave it to you to check that the norm squared of x plus alpha y wedge y is the same as the norm squared of x wedge y. Okay. Is this all right? Yeah. Okay, this you can check using the writing the norm squared as inner product with of a vector with itself and using bilinearity of the inner product. You can expand this out and you'll see that this expression remains unchanged if I replace x by x plus alpha y. Okay, so that means this sectional curvature is well defined. Is that clear? Yes?
Yeah, it's clear.
Okay, now geometrically, what is the meaning of this sectional curvature? Right, what is the meaning of sectional curvature? So let's look at what the expression is. So K sigma is inner product R xy x y over wedge x wedge y norm x wedge y squared. So let me suppose x and y are an orthonormal basis, then the denominator becomes 0, right? Sorry, 1. The denominator becomes 1. This x wedge y norm squared becomes 1. So this becomes just r xy x y if xy is an orthonormal basis of sigma. So what does this mean geometrically? Well, we saw what the curvature tensor was. It was given by infinitesimal parallel transport, right? So you have to take here, say you take the vector x. So you move in the direction of x, and here you have the vector y. So you take vector fields whose values at P are equal to X and Y. So say the vector fields are capital X, capital Y. You move in the direction of capital X, then capital Y, then minus X, then minus Y. And now what you do is you parallel transport this Rxy acting on X means you parallel transport X along this, right? So you parallel transport X. So maybe you come somewhere here, then you parallel transport X along this quadrilateral, you come here maybe, and then like this, and then. So maybe after the parallel transport, you come something like this, okay? And then the curvature tensor was given by, so R of xy was a limit t tends to 0, pt minus identity over t squared, right? So that means you have to look at the difference of this vector from the starting vector. You're looking at pt minus identity, right? So you look at pt of x minus x. So that's this difference, okay? So you take this difference, divide by t squared, you'll get some vector in this direction. So that will be something pointing in roughly the same direction as y. Then you take this inner product with y, you'll get something positive. So this is an example where the sectional curvature k sigma is positive. So how do you, so basically what you're doing is you parallel transport x along the quadrilateral, look at the change in x after parallel transport, and then take the inner product of that change with y. Okay. So, so for example, if we do this on the two sphere S2, okay. So suppose we parallel transport along geodesics. Okay, that might make it simpler. So yeah. So we know that these longitudes and the equator, these are geodesics, right, in S2. So suppose this is my vector x and this vector is my vector y. So I'm going to parallel transport along a small quadrilateral like this. Okay, I move along this equator. So the equator is a geodesic, and this is the tangent vector to the geodesic. So the parallel transport is just the tangent vector to the geodesic itself. Then I move up along the longitude. So that's a geodesic. Okay. So the parallel transport along a geodesic means you just keep the angle with the tangent vector to the geodesic constant. So if this angle is 90 degrees here, the angle here is also going to be 90 degrees. Okay. Right. And then I have the parallel transport along this curve, this latitude. This latitude is not a geodesic. Okay. So this is the only part where calculation needs to be a bit careful. What will happen is actually the after parallel transport, it will look something like this. So, so the angle will be a bit smaller than 90 degrees here. Okay. So, and then when you parallel transport along this longitude, this is again a geodesic, you'll come back here. Okay. So that means the this is PTX. So PTX minus X is points in this direction, upwards in the direction of Y. Okay, so in this case, your K sigma will be positive. Actually, you can show it's equal to +1. Okay, if n is equal to S2. Okay. So, see, what is it actually in 2 dimensions, right? This sectional which are along, right? Get infinitesimal rotation. If this is x, and I'm looking at this is ptx, right? So when I differentiate, this ptx will be, this will be orthogonal to x, you see? Okay, what I mean is this rxyx, this is going to be orthogonal to x, right? Because the curvature tensor is alternating in the last 2 arguments. So this is 0, right? That you can see in this picture. Ptx is moving along the circle. So when I let t tend to 0, I look at ptx minus x divided by t squared. That gives me a tangent vector which is tangent to the circle. So therefore, it's orthogonal to the radius vector, which is x, right? Okay. So that means this rxy in 2 dimensions, when n is equal to 2, then this rxyx, if xy is an orthonormal basis, this will be some multiple of y. That multiple is the sectional curvature. It's going to be k sigma y. Is that clear?
Yes, sir.
Because when I inner product with y, then the the inner product will be 1, right? So I'll just get k sigma, right? Is that clear? Okay, so this k sigma measures an infinitesimal rotation, right? It measures an infinitesimal rotation. So for another geometric interpretation, we can look at so the distance between geodesics. One second. Where did it go? Sorry, 1 second. And this seems to have disconnected. Yeah, okay. Yeah, okay. So another thing we can do is we take the vectors x and y, and then we take geodesics in the directions of x and y. Okay. So say this is x and this is y. And then I'm taking 2 geodesics in the directions of x and y. So let me call them, say, P sub t and Q sub t. Okay. So here PT, QT, these are geodesics such that, so ddt at t equal to 0 of PT is equal to x, ddt at t equal to 0 of qt is equal to y. And so xy are an orthonormal basis. So I can look at the distance between pt and qt, right? So if I look at this up to first order, this should look like in the Euclidean case, where these two will be sides of a right-angled isosceles triangle, right? So by Pythagoras theorem, this should be like square root 2 into t, right? So let me look at the distance squared, distance pt qt squared, okay? Well, it turns out that up to first order, we have the right approximation. This is 2 times t squared, okay? So this is what you would get in Euclidean space by Pythagoras theorem. But then we have a higher order correction term, which is some minus some positive constant c into the sectional curvature of sigma into t to the 4. Okay. And then there are higher order terms, order of t to the 5. Okay, as t tends to 0. Okay, here this c is some universal constant, positive constant. Okay. It's, I forget what it is exactly. That's why I'm just writing c. I think it's 1/3 or 1/6, something like that. Okay. I forget exactly what it is. So what does this mean? This means if the sectional curvature is positive, right, then up to higher order, at the next order term, the two geodesics converge towards each other. The distance is smaller than it would be in Euclidean space. Okay, so this is an example where sectional curvature is positive. Okay. On the other hand, if the sectional curvature is negative, then what will happen is my two geodesics, they will tend to diverge a bit further. So at second order, they diverge compared to Euclidean space. Okay. So this is PT, this is QT. So this is where the sectional curvature is negative. Okay. So an example of a negatively curved surface you can see here. You take a hyperboloid in R3, which looks like this. Okay. This will be a negatively curved surface. Okay. Here, I mean, the tangent space is two-dimensional. So sectional curvature, there's only one two-dimensional subspace, the whole tangent space. So sectional curvature is just the curvature of the surface is just the sectional curvature of the tangent space itself. Okay. So here you can see that these lines are geodesics. They diverge away from each other faster than in Euclidean space, right? Okay. You can see these geodesics are diverging away from each other, right? If I look here, then this little perpendicular will, if I move along, the distance will increase faster than in Euclidean space, right? Okay. Okay, so in positive curvature, geodesics tend to focus, like you can see in this example of the sphere. These geodesics they're converging towards each other. Okay. Whereas here, these in negative curvature, the geodesics are diverging away from each other. Can you see that? Yeah.
Yes, sir.
Okay. So just to give you some feeling for what sectional curvature is, apart from the definition. So yeah, geometrically it means in positive curvature, geodesics tend to focus, and in negative curvature, geodesics tend to diverge. So you can also look at it in terms of the distance function along between two geodesics. In negative curvature, this distance function is convex. So this is a convex function of t. Okay, you can see the convexity here. This is a convex function of t, right? The distance in the middle between these two geodesics will be less than half the average of these two distances. Okay, this distance function is convex. You see? Okay. So there's a convexity of the distance function in negative curvature or non-positive curvature in general. Whereas in positive curvature, the distance function will be concave. So I mean, so when the distance function is convex, in the middle, the two geodesics will come close to each other. Whereas when it's concave, in the middle, they'll be far apart. You see? Okay, so this is negative curvature. This is positive curvature. Okay. All right. So we don't have time to go into why the distance function is convex and so on. So that needs some calculations, which we haven't developed the machinery for that. Okay. So that's just a brief introduction to sectional curvature. And then the next object which will be important for us is what's called Ricci curvature. So this is a bit more abstract. So the Ricci curvature is actually related to changes in volume, how the volume grows. So, but we won't have time to explain that either. So I'll just have to give you the definition. So the Ricci curvature is first of all defined as a bilinear form on the tangent space. So it's a map from TPM cross TPM to R. You take a pair of tangent vectors XY. So once I have two tangent vectors XY, that gives me a linear map from the tangent space to itself. Z goes to R of X, Z, Y. So here X and Y are fixed. Z is varying. So this is a linear map from the tangent space to itself. It's an endomorphism. Therefore, I can take its trace, right? So I take the trace of this linear map and then I divide by n minus 1. Okay, so this is the Ricci curvature. It is a bilinear form on the tangent space, right? This is bilinear in X and Y. Okay, so there's less than a minute. Let me stop this session and start a new one. Okay. Okay. Right. So let's look at Ricci curvature. So Ricci curvature is defined to be this bilinear form on the tangent space, right? XY goes to the trace of the linear map. Z goes to R of X, Z, Y. This trace divided by n minus 1. So why are we dividing by n minus 1? Because actually what we'll see is that this can be seen as an average of sectional curvatures, of n minus 1 sectional curvatures. We'll come to that in a second. First, we want to see that actually this is a symmetric bilinear form. Okay. So how do we compute this? Well, this is a trace. So the trace we can compute using any orthonormal basis, right? So if I take n minus 1 times the Ricci curvature of xy, then this is a trace of this linear map. So the trace I can compute by letting the linear map act on basis vectors EI and then taking inner product with EI, right? So the linear map acting on EI is R of X comma EI Y and then inner product with EI, right? So this in our earlier notation, this is round bracket X EI Y EI. And now I use the fourth property of the curvature tensor that when I take 4 arguments, if I put the first 2 arguments in the last 2 spots and the last 2 arguments in the first 2 spots, right? Then the curvature tensor is unchanged under this permutation. So XYZT is the same as ZTXY. So if I apply that here, the X and EI I can put in the last 2 spots and the Y and EI I can put in the first 2 spots. So this then becomes, as we can see, the Ricci n-1 times the Ricci curvature of Y comma X, right? Is that clear? Yes?
Yeah, it's clear.
So therefore, the Ricci curvature is a symmetric bilinear form. So we've used this last property of the curvature tensor here, that XYZT is equal to ZTXY, okay? So we've used that property. So the Ricci is a symmetric bilinear form. So since it's a symmetric bilinear form, it corresponds to a self-adjoint linear map, right? From the tangent space to itself, right? Such that this symmetric bilinear form, Ricci of XY, is given by the inner product of this endomorphism Ricci acting on X, inner product with Y, right? Yeah, remember there's on an inner product space, there is a one-to-one correspondence between symmetric bilinear forms and self-adjoint linear maps, right? Any self-adjoint linear map, say T, gives you a symmetric bilinear form. XY goes to inner product of TX with Y, right? That is the correspondence. Every symmetric bilinear form is of this form. XY goes to inner product TX with Y for some self-adjoint linear map T. Okay, some unique self-adjoint linear map T. So in this case, we can think of the Ricci curvature also as a self-adjoint linear map. Okay. All right. Now, since it's a symmetric bilinear form, by the polarization identity, it's determined by its values on the diagonal, right? It's determined by the corresponding quadratic form, Ricci of V comma V. So let's compute Ricci of V comma V. How do we do that? So let's take a non-zero vector V, okay? So then what we can do is we take E1 to En-1 to be an orthonormal basis of V perp, of the orthogonal complement of V, okay? So then if I add the vector V divided by norm V to this orthonormal basis, I'll get an orthonormal basis for the whole tangent space, right? So then what will my Ricci curvature be of V comma V? So it's 1 over n-1 into a trace. So that trace is going to be round bracket V with the first basis vector, that is V over norm V, comma V with the first basis vector, V over norm V. So this is 0 because I have a V and a V here, and this is alternating in the first 2 arguments. So this first term is 0. Then there are n-1 terms left of the form VEI comma VEI, right? So this first term vanishes. What are these last terms? These last terms, if I divide it by norm V squared, then I would get exactly the sectional curvature. So this term is nothing but the sectional curvature of the 2 planes spanned by V and EI into norm V squared. Okay. So the Ricci curvature of V comma V is norm V squared into an average of sectional curvatures, 1 over n-1. Some I goes from 1 to n-1, sectional curvature of V comma EI. Is that clear? Yeah, so in the picture, what you have is Yeah. So Ricci curvature. So here is V, and then I'm taking the orthogonal complement and a basis for that. So that would look like this: E1, E2, right? So I take this two plane spanned by V and E1. So that looks like this. And then I also take this two planes spanned by 2. So that looks like this. And then I add up the sectional curvatures of these two and I take their average. Okay. And I multiply. So suppose V is a unit vector. Okay. So then Ricci of VV will be 1 over n minus 1 k sigma 1 up to k sigma n minus 1. Okay, sigma I is equal to span of VEI, where E1 to En minus 1 is an orthonormal basis of V perp. Is this clear? Yes?
Yeah, it's clear.
Okay. So what can we say if we have a lower bound on sectional curvature? So suppose K sigma is greater than or equal to some constant, say lambda, okay, for all sigma, that implies that Ricci of V comma V, this will be greater than or equal to lambda norm V squared, right? Is that clear? So the linear map Ricci, if I think of the self-adjoint linear map, if lambda is positive, for example, this will be positive definite, right? So this will be greater than lambda times identity. Okay. What this means, when I write that one self-adjoint linear map is greater than another, A greater than or equal to B, means that A minus B is positive semi-definite. Okay, that's all it means. Is this clear? Yes?
Yeah, it's clear. Yeah.
Okay. Okay. All right. So, for example, there are some interesting manifolds, like say in S2. In S2, actually, the sectional curvature is constant equal. Well, S2 is a bit of a trivial example, it's two-dimensional. If I take the n sphere, Sn in Rn plus 1, it turns out the sectional curvature is constant on two planes. So that implies that this Ricci curvature, right, this will be it's constant equal to 1. So this Ricci curvature of VV will be just norm V squared. Okay, so this Ricci endomorphism will be just the identity endomorphism. Okay. And yeah, so for a manifold of constant sectional curvature, that means that all the sectional curvatures of all two planes are equal to some constant. The Ricci curvature is a constant multiple of the identity. Okay. Or if you want to think in terms of the bilinear form, then the Ricci curvature, that 2 tensor, is a constant multiple of the metric, right? It's just some constant times norm V squared. So it's a constant multiple of the Riemannian metric. Okay, so such manifolds where the Ricci curvature is a constant multiple of the metric, these are called Einstein manifolds. Okay, so just a little remark. So if sectional curvature is equal to a constant C for all sigma, then that implies that Ricci of VV, this is constant equal to C norm V squared, right? So that implies that this Ricci curvature is C times the metric G. Okay, G equal to Riemannian metric. So such a manifold is called an Einstein manifold. Okay. All right, so that's a little bit about Ricci curvature. This will be important for us later, this Ricci curvature. Okay, so now I want to come to energy. Okay.
Sir, is the Ricci curvature like the mean curvature that we had in differential geometry of surfaces?
Right. No. See, the mean curvature depends on your embedding into 3 space. It's not an intrinsic quantity like the Gaussian curvature. Okay, the Gaussian curvature is exactly the sectional curvature. This is intrinsic. All right. The Gaussian curvature is exactly the sectional curvature. But the Ricci curvature is also intrinsic. So in 2 dimensions, the Ricci curvature equals the sectional curvature, right? So for a surface, it's the same as the sectional curvature, which is the Gaussian curvature. Right. If n is equal to 2, then this is just k sigma, right? K sigma 1. You take V and EI is just a vector orthonormal to V, right? So you just get one sectional curvature. It's just Ricci curvature is the same as the sectional curvature, right?
Yeah.
It's just the same as the sectional curvature. So yeah. So no, it's not the mean curvature. No. Mean curvature is what? It's the trace of the second fundamental form, right?
Yes.
It's the sum of eigenvalues of the shape operator, right? It's the sum of eigenvalues of the shape operator. So the shape operator is a self-adjoint linear map on the tangent space that corresponds to a symmetric bilinear form called the second fundamental form of the surface. That second fundamental form depends on the embedding of the surface into R3. Okay, it's not an intrinsic quantity. And Gauss's theorema egregium says that even if the second fundamental form is not intrinsic, right, the determinant of the second fundamental form, that's the Gaussian curvature, that is intrinsic. So that does not depend on the embedding, right? That is Gauss's, theorema egregium, if you remember. Do you remember that?
Yes. Yeah.
Right. So the determinant is intrinsic, but the trace is not intrinsic. All right.
Yeah.
Okay. The trace is not. I mean, just think of just the Gaussian curvature measures isometric when two surfaces are isometric if and only if they have the same Gaussian curvature. So for example, if I take a cylinder, right? So then at any point, the two principal curvatures, one principal curvature in this direction is 0, and the other is say +1 in this direction. Yeah, these are the eigenvalues of the shape operator, the eigenvectors and eigenvalues, right? So here, the sectional curvature is the determinant. It's 0 into 1, which is 0, right? Whereas the trace of the shape operator is 0 plus 1, which is 1, right? And this cylinder is isometric to a flat plane, where both eigenvalues are 0, 0 and 0. So here, this Gaussian curvature is 0 into 0, that is still 0. But now the trace is also 0. Right? So the trace is not intrinsic. What I mean is there is a map from this 2-plane into this cylinder, right? You wrap the plane around the cylinder, a map which is an isometry. What is an isometry? That means it preserves lengths of curves. Okay, so lengths of curves are preserved. That means lengths of tangent vectors are preserved, right? So that is something intrinsic, right? It's preserving the Riemannian metric here, the induced Riemannian metric. Is it clear? But these are two different embeddings, right?
Yeah, okay.
Okay, so the mean curvature is not intrinsic, it is extrinsic. It depends on the embedding. You can see with a different embedding, the mean curvature is changing, right? Is it clear?
Yes.
Okay. Okay, yeah, so Ricci curvature, no, in 2 dimensions, it's just the same as the sectional curvature, which is the same as the Gaussian curvature, okay? All right, okay. Okay, so let me come to what will be a main topic of the rest of the course, something called energy. So, suppose gamma is a C1 curve in my Riemannian manifold M, then we define the energy of gamma to be half the integral from A to B of norm gamma prime squared dt, okay? So, I mean, the reason for the name energy, I suppose, is because this norm gamma prime squared, right? This you think of as the velocity squared, right? So you have the formula for kinetic energy, half mv squared. So if you take m in equal to 1 unit mass, then this is half v squared, right? Half the velocity, norm of the, half the speed squared. So this is energy, okay? And then you're integrating this energy over the curve, all right? So why is this energy important? Well, remember we showed much earlier that if I was looking at a submanifold of Rn, right, we derived the geodesic equation by looking at length minimizing curves, right? So then what we were doing is we were looking at the length, that is the integral of norm gamma prime. And we showed that if gamma is a unit speed curve, so it has constant speed, and if it is length minimizing, then by looking at variations of gamma, we showed that gamma has to satisfy the geodesic equation, right? The covariant derivative d gamma prime dt has to be 0. Right? We showed that, yes? Okay. So actually, there we had to assume that the speed was constant, okay, when we were looking at length minimizing curves. So minimizers of length satisfy the geodesic equation, right? So the geodesic equation you can think of as the Euler-Lagrange. Well, okay, you have to be a bit careful. If you restrict to unit speed curves, then the Euler-Lagrange equations are the geodesic equations. But for the energy, if I look at this energy functional on curves, then actually we do not need to assume anything about the parametrization. It turns out the Euler-Lagrange equations for the energy functional are exactly the geodesic equation. d gamma prime dt equal to 0. Okay. So we're going to see that as follows by looking at variations of energy. Okay. Right. Remember, when you derive the Euler-Lagrange equations, you have to differentiate the functional with respect to a variation, right? So have all of you seen the calculus of variations in some form or the other? Hello?
No, sir, we haven't seen.
Oh, you don't know what the Euler-Lagrange equations are?
Uh, in
We've
classical,
seen it in classical mechanics.
in
Yes,
long
classical
yes,
mechanics.
yes. It's a very classical topic. I mean, yeah, so. Yeah. Okay, I'm surprised. I thought in your ODs course you would have seen the Euler-Lagrange equations. At least in ODs you see it often. So, okay. All right, yeah. So, I mean, the Euler-Lagrange equations lead to certain ODs. So, yeah. Okay. It's just the equation that you get by looking at a minimizer of a functional, differentiating the functional. What you're doing is you're setting the derivative of the functional equal to 0. Okay, you think of this energy as a function on an infinite dimensional space, say a space, well, it's a nonlinear space, a space of curves, and then you're differentiating the energy. Okay, so the derivative of the energy is a linear map on an appropriate space. Okay. And you set that at a critical point, a point where the energy has a local minimum or maximum, right? You set the derivative equal to 0, right? So that gives you some equation. And that equation is the Euler-Lagrange equation. So we'll see what we get. So first, let's look at a variation of a curve. So what is a variation? It means a smooth map from an interval minus epsilon epsilon cross AB into M, such that at time 0, f of 0 comma t is gamma t for all t. Okay. And for other s in the interval minus epsilon to epsilon, you have a one parameter family of curves, gamma s, where gamma s of t is f of s comma t. Okay. All right. So you have this one parameter family of curves, which when s is equal to 0, it gives you the curve gamma. Okay? So this is a smooth variation of gamma. And we say that the variation is a proper variation if the endpoints remain fixed throughout the variation. Okay, so gamma s of A is equal to gamma of A for all s, and gamma s of B is equal to gamma B for all s. Okay. So then, like we did earlier, the variational vector field of F is the vector field V along gamma, which you get by differentiating with respect to S at time 0, at time S equal to 0. Okay. So it's del F del S of 0 comma t. So this is a tangent vector at gamma t, right? Okay. So then we have, a following lemma that if I choose any smooth vector field V along gamma, then there is a variation of gamma whose variational vector field is equal to V. Okay, so every vector field along gamma occurs as the variational vector field of a variation of gamma. Okay. And if the vector field vanishes at A and B, then the corresponding variation you can choose to be proper. So it sorry, just 1 second. I have to attend to the door. Just 1 second. One second. Sorry. Okay, so yeah. Okay, so here's the picture. You have a curve, say this is your manifold. So we have a curve here, gamma. And then a variation would be a one parameter family of curves. So, well, this is not a good example for a proper variation. So let me take a curve like this. So this is my gamma, and then I have a one parameter family. So this would be a proper variation where the endpoints are fixed. Okay. So this is my gamma S, and this is my gamma 0, which is gamma. Is this clear? And then if I fix T and differentiate with respect to S, then I'll get my variational vector field. Okay. This is my variational vector field. So this is what I get when I differentiate with respect to S. So because the endpoints are fixed, at the endpoints, the variational vector field is 0, right? So VA is 0, VB is 0. If gamma S is a proper variation. Okay. And conversely, what we're saying is that given any vector field V along gamma, we can choose a variation whose variational vector field is equal to V. And if V vanishes at the endpoints, then the variation we can choose to be proper. Okay, so the proof is quite straightforward. Let me just give you the idea. And to save time, I won't go through the exact proof. It's very simple. The variation is basically what you do is you put f of st to be the following. So I want to construct a variation of gamma, right? So at a point gamma t, I have my vector v, vt. This is gamma t. So I want, if I fix t and vary s, I want to get a curve whose s derivative with respect to s is equal to v. So the one natural choice is you just take the exponential map, right? And take the geodesic with initial condition v of t, right? So what is that geodesic? That is the geodesic s goes to x sub gamma t of s of vt. Okay, is it clear? Yeah, if I differentiate this with respect to s at time s equal to 0, I'll get back vt, right? So my variation is simply f of st is equal to x sub gamma t of s of vt. Okay. Now the only thing that you have to check is that there is some interval minus epsilon to epsilon for which this is well defined. I mean, this is only an issue if the manifold is not complete. That is, if the exponential map is not defined on the whole tangent space at each point. So if the manifold is compact without boundary, then there's no problem. The exponential map is defined on the whole tangent space. The only thing I've done in this lemma is just to be a bit careful that if the manifold is not complete, then this will still be well defined defined for S small enough, right? This will still be well defined for S small enough because the exponential will be defined in small neighborhoods of the origin and the vector field V is bounded. So if I take S very small, then S times V will be small and it will be small enough so that it lies in the domain of the exponential map. That's the idea of the lemma. Okay. Is it clear?
Yeah.
Okay. So I've written out the details here. You can look at the details. I'm going to skip this proof for the sake of time. Okay. So just have a look. It's not very difficult. And you can see from this formula, if the variation is proper, that is, if VA is 0, then this will be constant in S, right? At time A, for T equal to A and B. Okay. All right. Yeah. Okay. So there's a correspondence between vector fields along gamma and variations of gamma. You can think of a vector field. I said this earlier at some point. A vector field along the curve, you can think of as an infinitesimal variation of the curve. It gives you a direction in which to deform the curve at each point, right? So it's an infinitesimal variation of the curve. That is what a vector field along a curve is. Okay. So now we can derive what you can think of as a formula for the derivative of the energy functional. So what is that? That's called the first variation of energy. So let F be a variation of gamma with variational vector field V. Okay. So then we have this formula that DDS at S equal to 0 of the energy of gamma S is minus the integral from A to B of V inner product with D gamma prime dt, integral dt, plus two boundary terms, VB inner product gamma prime B minus VA inner product gamma prime A. Okay. Okay. So let's compute this. So the derivative of the energy will be what? By differentiation under the integral sign, I can write this as half the integral from A to B of DDS at S equal to 0 of the inner product of, what was it? Gamma S prime T, gamma S prime T, right? That's the energy of gamma S. So the gamma S prime is what? It is del F del T, right? Yes? Okay. So this is half the integral of the derivative with respect to S of del F del T dt. Okay. So now by metric compatibility, this is going to be twice the inner product of the covariant derivative d sub del S at S equal to 0 of del F del T inner product with del F del T. So the 2 and the half will cancel. Okay. All right, up to here? Yes?
Yes, sir.
Now, this F is a parametrized surface. And last time we showed that we talked about how the symmetry of the connection implies the property that d del S del F del T is the same as d del T del F del S, right? So we can interchange these two S and T derivatives. So this I write as d del T of del F del S at S equal to 0. Now, what is del F del S at S equal to 0? By definition, that is the variational vector field V. And then I'm taking d del T of that. So this becomes dV dt, right? And this del F del T at S equal to 0, that is gamma prime, right? So finally, I get this is the integral of inner product dV dt with gamma prime, right? Okay. Now, we can do an integration by parts here. So this, by metric compatibility, this inner product of dV dt with gamma prime, I can write as ddt of inner product V gamma prime minus inner product of V with D gamma prime dt, right? Is that clear?
Yeah, that is clear.
Yeah, when I do ddt of this V gamma prime, I'll get two terms, right? One will be this term, dv dt inner product gamma prime. The other term will be exactly this v inner product d gamma prime dt. So if I subtract that, then I'll get exactly this term, dv dt inner product gamma prime. Okay. So now I have this. So this, by the fundamental theorem of calculus, this first term I can integrate. That will give me these two boundary terms. And the rest is what I wanted. This is minus the integral v d gamma prime dt dt. All right. Is it clear?
Yes.
Yes?
Sir.
Yeah. Fine. So that proves the first variation of energy. And this is enough to prove that a curve is a geodesic if and only if the derivative of the energy is 0 for any proper variation of gamma. Okay. If I take any proper variation of gamma, then the derivative of the energy has to be 0, and vice versa. If the derivative of the energy is 0 for any proper variation, then gamma is a geodesic. Okay. So, well, one direction is clear. If gamma is a geodesic, then d gamma prime dt is 0. So therefore, the derivative of the energy, notice if the variation is proper, then these two boundary terms vanish, right? VB and VA are 0, so the boundary terms vanish. So you just have this integral. So the derivative of the energy is minus this integral a to b v d gamma prime dt. So this is 0 because gamma is a geodesic. So d gamma prime dt is 0. All right. So if gamma is a geodesic, then it is a critical point of the energy functional. Okay. You can think of it that way, right? And conversely, suppose the derivative of the energy is 0 for all proper variations of gamma, then you can show that gamma is a geodesic. Essentially, what that will mean is what? If the derivative of the energy is 0 for all proper variations, right? We know that given any vector field v along gamma, right? We can choose any vector field which vanishes at the endpoint. We can choose a proper variation whose variational vector field is equal to that given vector field v. So if the derivative of the energy is 0, then by the first variation formula, that will mean that the integral a to b of v d gamma prime dt. Okay. All right. So if the derivative of the energy functional is 0 for all proper variations, then using the first variational formula, that means for any vector field v along gamma, the integral of the inner product of v with d gamma prime dt, that is 0, right? And that, once you know that's true for all vector fields v along gamma, then it's easy to show that d gamma prime dt has to be 0, right? Okay. So how do you do that? You just choose the vector field v so that this inner product with d gamma prime dt is positive everywhere. Okay. So what you do is you take a g, a smooth function, a non-negative function, which is 0 at the endpoints of the interval AB, and which is positive inside the open interval AB. And then you take VT, your vector field, to be GT into d gamma prime dt, right? So we know that this vector field, because it vanishes at the endpoints, we get a corresponding proper variation of gamma, whose variational vector field is equal to this VT. And so then, by hypothesis, the first derivative of the energy is 0. That means the integral of v d gamma prime dt, this inner product, the integral is 0. This inner product is just integral of the function g times norm d gamma prime dt squared. And g is positive on the open interval AB. So that means that this d gamma prime dt has to be identically 0 on the open interval AB. And therefore also on the closed interval AB, since gamma is C2. And thus gamma is the geodesic. Is this clear? Yes.
Yeah, it's clear.
It's clear? Yeah. Okay. Right. Okay, so that's what I meant when I said the Euler-Lagrange equations for the energy functional, they lead to gamma being a geodesic. So notice that a critical point of the energy functional, a local minimum, right? If you have an energy minimizing curve, it will be a geodesic, right? And so it will automatically have constant speed. Remember, we showed that geodesics have constant speed, right? So this will automatically have constant speed. So in a sense, it is better than the length functional, right? The length functional was the integral of norm gamma prime. The energy functional is the half the integral of norm gamma prime squared. So the Euler-Lagrange equation for the energy functional is exactly the geodesic equation d gamma prime dt equal to 0. Okay.
So this energy functional, if it has local extrema, they are always local minima, right? Because they
Correct. That is true. Yes. In fact, yeah, that's true. Well, not exactly. No, that's not true. That's not true. No,
because it has to be a geodesic, right?
Yeah, but geodesics are only locally length minimizing. So it will be true for small geodesics. But if I take a long enough geodesic, then the energy functional, it could have a maxima. So that depends on the curvature. Okay, so what happens is in negative curvature, the energy functional you can show is actually a sort of, it has a convexity property. So you know that if I take a convex function at a minimum, at a local, at a critical point, it has a minimum, right? So in negative curvature, what will happen is, so in negative curvature, this geodesic in the middle of this negatively curved surface, this has minimum energy, okay? And also shortest length. So amongst geodesics which are freely homotopic to it, okay. But in positive curvature, like this, you can have a geodesic which has this closed geodesic, it will have maximum length in the homotopy class. Well, I mean, yeah. Well, if I take, well, not maximum length as such, it's a bit more complicated than that, but maximum amongst geodesic variations. So if I vary this sort of parallelly amongst geodesics, then yeah, the lengths will decrease. So yeah, actually in positive curvature, it's one can't really say anything. In negative curvature, one can say that in every free homotopy class of closed curves, there is a unique closed geodesic, which is the unique minimum energy curve in that homotopy class. Okay. So we did a, so let me give you an exercise here. For a free homotopy of closed curves, gamma S, so say from 0, 1 to M, so here what you want is that so gamma S of 0 is equal to gamma S of 1, and also the tangent vectors are the same. So gamma S prime 0 is gamma S prime 1 for all S. Okay. Then compute the variation of energy. You'll see that the boundary term vanishes. Okay, when you take a free homotopy of closed curves. So this will be just minus the integral 0 to 1 inner product of V d gamma prime dt. Okay. Okay, the fact that these are all closed curves will mean actually that the boundary terms will vanish. Okay. All right, so try and do this exercise. Okay. So this will mean that if I take a curve of minimum energy in the free homotopy class, like in this picture, then the derivative of the energy will be 0 there, right? And so therefore it has to be a geodesic. So this is one way that one can show that in any closed manifold, any free homotopy class of closed curves contains a closed geodesic. Okay. So a closed geodesic means a periodic geodesic, one which satisfies these two conditions. Okay. So I need the condition on the tangent vectors as well, because I want the curve when it closes up to be a smooth curve. This will not be smooth, right? The tangent vectors are different. What I want is a smooth curve. So the tangent vectors are the same. All right. Is it clear?
Yeah, it's clear.
Yeah.
So what was the conclusion from this exercise? Can you say that again?
Yeah, the conclusion is that we won't prove this, but one can use this idea of energy to prove this, that any free homotopy class of closed curves in a closed manifold, so that means compact without boundary, contains a closed geodesic. Okay, so this gives a way to
But for this closed geodesic to have minimum length, for that you might need negative curvature. Is that what you said before that?
No. It will also have minimum length. So let's just see that. So minimum energy will imply minimum length. Also.
No, okay. I got
Yeah.
confused.
So that actually follows from Cauchy-Schwarz.
Yeah, of course it will have minimum length.
No. Well, it's not clear. There's a little argument for that. So let me give the argument. So suppose you take a C1 curve. Okay. So then let's apply Cauchy-Schwarz to the length integral. So if I look at the length squared, this is the integral from 0 to a norm gamma prime t dt whole squared. So by Cauchy-Schwarz, this is less than the product of integrals from 0 to a norm gamma prime t squared into integral from 0 to a 1 squared dt, right? So this becomes a times twice the energy. Okay, so the length squared is less than or equal to 2a times the energy. Yes. Okay. And we know that equality occurs in Cauchy-Schwarz if and only if this function is constant, right? I mean, these two functions, norm gamma prime and the constant function 1, have to be linearly dependent. That means that norm gamma prime has to be constant, right? Okay. Yeah. If and only if C is also a minimizing geodesic. All right. So any minimizing geodesic from P to Q, length minimizing geodesic, will also be energy minimizing. Okay. All right. So since gamma has constant speed and is length minimizing, gamma is a geodesic, right? So we know that then we have the equality in Cauchy-Schwarz. So 2a times the energy of gamma is equal to the length of gamma squared. So since gamma is length minimizing, this is less than or equal to the length of c squared. And that by Cauchy-Schwarz is less than or equal to 2a times the energy of c. So you cancel the 2a from both sides and you get that energy of gamma is less than or equal to energy of c. Okay. Now, if equality holds, then these two are equal. The length of c squared has to equal twice a times the energy of c. So that means that c has constant speed, and also the length of c has to equal the length of gamma because you have equality here, and that's equal to the distance pq. So that means that c has constant speed and is length minimizing, therefore it is a geodesic. Okay. So constant speed, length minimizing curves are geodesics, right? So therefore, any minimizer of the energy will be so any minimizer of the energy will be also a length minimizing geodesic, right? See, what this is showing is that if I take a length minimizing geodesic from P to Q, then it has minimum energy, right? Amongst all curves from P to Q. Okay. And if I take any curve from P to Q, C, whose energy is equal to the energy of gamma, that means the energy is equal to the minimum energy. So therefore, if it is a minimizer of the energy amongst curves from P to Q, then it has to be a length minimizing geodesic, right? That's what we're showing. Is that clear? Yeah, so the argument we're using is that by Cauchy-Schwarz, it has to have constant speed. And because the length is minimum, a constant speed length minimizing curve has to be a geodesic. But this argument, to show that it's a geodesic, actually we could use a variational argument. We know that the energy is the minimum amongst all curves from P to Q. So we could choose a variation for any variation of C, right? For any variation of C, the derivative of the energy will be 0. And then you use the first variation of energy formula. That means that the covariant derivative dc prime dt will be 0. Okay, and so C will be a geodesic. Is that clear? Yes? Yes, is that all right?
Yeah, it's okay.
Right. So, okay, and conversely, if C is a length minimizing geodesic, then C has constant speed because it's a geodesic. So we have equality in Cauchy-Schwarz. 2a times energy of C is equal to length of C squared. And if C is length minimizing, then length of C squared is equal to length of gamma squared. And that is equal to 2a times energy of gamma. So therefore, energy of C is equal to energy of gamma. Okay. So yeah, if we look at curves from P to Q, then the length minimizers with constant speed are the same as the energy minimizers. Is that clear? Both of them are length minimizing geodesics from P to Q. Is it clear?
Yes, sir.
Okay, so yeah. Okay. So try and prove an analog of this. So this is, you can think of this as curves with endpoints fixed, right? So we're looking at all curves with fixed endpoints. Instead of fixing the endpoints, you can try looking at a homotopy class of closed curves, okay? And try and prove the same result, all right? Does that make sense? Yeah.
Yeah.
Okay. All right. So try and prove the same result when you have a free homotopy class of closed curves. Okay. Okay. So I'll leave that to you. Yeah. So, so this was energy of curves, right? Now, we were talking about the Laplacian. So I just want to finish today by saying how the Laplacian comes up when you look at the energy of functions. So suppose f is a smooth function on M. So then doesn't have to be smooth, even C1 is good enough. So, but let me just assume smooth for the moment. So, then the energy of F is defined to be half the integral over M of the norm of the gradient vector field squared with respect to volume measure on M. Okay. Is the definition clear? Okay. So for simplicity, let me assume that M is closed. So compact without boundary and oriented. Okay. So then we have a volume form. Okay. So this integral will be finite because M is compact and F is smooth. Okay. So this is the energy of a function. Actually, if I want something interesting, let me take M to be compact with boundary. Let me take M to be, yeah. So we can talk about the closed case too, but let me just talk about it. Compact with boundary. So let me just explain how consideration of energy leads to harmonic functions. So you try and solve the Dirichlet problem. So you're given phi a continuous function on the boundary of M. Okay. Then minimize energy of F over F smooth on M and continuous on the closure such that the boundary value of F is equal to phi. Okay. So I'm fixing the boundary value of my functions and then I'm trying to minimize their energy. Okay. All right. So suppose that F is a minimizer of the energy subject to the boundary condition F equal to phi on the boundary. Then we will show that F has to be harmonic. Okay. And so then F will become actually the harmonic extension of this function phi to the manifold M. Okay, and it will be a solution to the Dirichlet problem in the sense that we spoke of last time. That is the harmonic extension of a continuous function on the boundary. Okay. So suppose F is a minimizer. Okay. Then what we can do is the following. Given any variation of f, so again we look at variations. Okay, so ft, or let me call it fs. Okay, so fs, these will be functions from m to r. So now the variation is by a family of functions. Okay, so what I want is that all of these functions are fixed on the boundary. So fs restricted to boundary m is equal to 5 for all s. Okay, and then you let, so now instead of a variational vector field, you'll get a variational function, right? So we let v of x, right? This will be what? Del del s at s equal to 0 of fs of x, right? So this is a function, right? Okay, v is a function on m. So this is the variational function now. Is that clear? Yeah. So let me compute the variation of energy, right? So what is dds at s equal to 0 of the energy of fs? Okay. Well, by differentiation under the integral sign, this is half the integral over m of dds at s equal to 0 of norm gamma prime squared. So that is norm grad fs squared. So that is inner product of grad fs with grad fs. Okay. d vol m. And now this is half by metric compatibility. This will, the derivative of this inner product will be twice inner product of d del s, the covariant derivative, right, of grad fs at x, grad f at x, right, d vol x. Yes. Now, this derivative is actually just the normal derivative, because grad fs at x, these are all in the same tangent space, txm, right, for all s. So if you're inside a fixed tangent space, right, then the covariant derivative is just the usual derivative inside that vector space, right, inside this tangent space. Yes? Right. Yes?
Yeah.
And so this d del s at s equal to 0 of grad fs at x, this is just del del s at s equal to 0 of grad fs at x. And now the gradient, if I think of it as an operator on functions, right, this is linear on functions, right? So this del del s of grad fs will be what? It will be grad fs minus grad f0, right? So that is grad of fs minus f0, and then I divide by s. So fs minus f0 over s, that converges to this function v, and I have the grad outside, right? So this, when I take the derivative, this will converge to grad v at x, right? Okay, so this will just be grad V at x. So, and this 2.5 will cancel. So what I get is integral over m inner product grad V grad F. Okay. Yes. All right. Yes.
Yes, yes, yes.
Okay, now we can again do an integration by parts here, like we did in the energy integral for curves. We did an integration by parts. Here again, we just do an integration by parts. So for that, we use this following formula we had for the divergence, the Leibniz rule for the divergence, right? So divergence of a function psi times a vector field x was inner product grad psi with x. So that means you differentiate psi first, keep x fixed, and then you take psi and you differentiate x, so you'll get psi divergence x, right? We proved this formula. So now you take, so if I have this inner product grad V grad F, I can put x equal to grad F, right? So if I put x equal to grad F, and psi is equal to V, right? Then what do I get? I get that divergence of V grad F is equal to inner product grad V grad F plus V divergence of grad F. What is the divergence of grad F?
Laplacian.
Laplacian, right? So I get this formula. Okay, so I substitute this above here. So this becomes now the integral over m of divergence V grad F minus V Laplacian F d vol, right? Okay. So now by the divergence theorem, I can integrate the first term. So this will become integral over boundary M, right? The inner product of V grad F with the normal vector ds, right? Minus, I get the integral over M of V Laplacian F d vol. Is this clear? Yeah.
So that term will be 0, right? There's no boundary.
Correct. Yes, this term is 0. Why? Because V restricted to boundary M is what? It is del Fs del S at S equal to 0 restricted to boundary M, right? But on boundary M, all my functions Fs were constant in S, right? Equal to phi. They're all equal to phi on boundary M, right? So when I differentiate in S on the boundary, I'll get 0. So this term is 0, okay? So therefore, I just get this minus integral over M V Laplacian F d vol M. Okay. So thus we get DDS at S equal to 0 of energy of Fs is minus integral of the variational function now into the Laplacian of F. So do you see a formal similarity with the variation of energy for curves, right? There, the second derivative was played by d, the role of second derivative was played by d gamma prime dt. Here we get a second derivative term, it's the coming from the Laplacian, okay? Right. But the formulae are similar, right? You can see the similarity. Yeah?
Yeah.
Right. we'll see that these are both special cases of a general formula actually for maps between manifolds. Okay. So these are both special cases of a general formula. Okay. So if F is a minimizer, so if F minimizes energy subject to F restricted to boundary M equal to phi, then the derivative of the energy is 0 for all variations, right? So this is minus the integral of Laplacian of t for m. And here, given any variational function, I can always construct a variation whose variational function is that function, right? I just take f plus tv, right? So this is true for all functions v in C infinity m, such that v restricted to boundary m is 0, right? So if this is true for all such v, then that implies by a standard argument that Laplacian f is 0, right? Is it clear? So f is harmonic. Okay. All right. So what we see is that minimizers of energy if I take my map to be a curve from an interval into my manifold, then minimizers of energy are geodesics, right? In this case, we get geodesics. Whereas if I look at the sort of dual situation where I have a function, so that's a map from the manifold to the real line, then minimizers of energy are harmonic functions. Okay, so to finish, what the remainder of the course, what we'll be looking at is actually maps between manifolds. So that's a fully nonlinear version of the above two situations, right? So say a map between manifolds like this, then we can define the energy of such a map, and then we'll see that minimizers of the energy in this nonlinear setting, fully nonlinear, are what are called harmonic maps. Okay, so harmonic maps, they will arise as minimizers of the energy or critical points of the energy in general, and you can think of them as a common generalization of both geodesics and harmonic functions, where now both the domain and the range become manifolds. Okay, so we'll start talking about harmonic maps on Friday. Okay, is it clear?
Yeah, it's good.
Okay, so these will be a common generalization of both geodesics and harmonic functions. Okay, so those will be harmonic maps. Okay. Okay, so let me stop here and I'll see you Friday.